Welcome to The Explainer. I'm your host, and as a battle-tested data scientist who frankly spends every single day in the trenches with these algorithms, I am here to give you a high-yield, no-nonsense crash course on the four major families of AI models. If you want to absolutely ace your metaphorical exam and truly understand how the entire artificial intelligence landscape is mapped out, well, you are in the exact right place. We are going to translate all that dense, intimidating math into clear, actionable concepts.
So here is your syllabus for today's review session. We are covering four main chapters: classical machine learning, deep learning neural networks, generative AI, and finally, reinforcement learning. Let's just jump right in.
Chapter 1. Classical Machine Learning. This is where we look at structured data algorithms. All right, so picture your neat, perfectly structured spreadsheets. We can basically split this chapter into two core concepts that you absolutely need to have memorized. First up is supervised learning. This is where we play the role of a teacher, training the AI using clearly labeled examples so it can eventually make its own predictions. On the flip side, we have unsupervised learning. This is where we hand the AI completely raw, unlabeled data, and we ask it to act like an explorer, just hunting for hidden patterns entirely on its own. Okay, here is your first major cheat sheet. Notice how we use linear regression when we want to predict a continuous number, like, say, estimating a house's price based on its square footage. But if we want to predict a binary category, like figuring out whether an incoming email is spam or not spam, we switch over to logistic regression. Now, decision trees are beautifully simple. They just make predictions by splitting data through a series of if-then questions. Then we have support vector machines, or SVM, which find the optimal mathematical boundary to separate different categories of data in really complex spaces. And of course, naive Bayes, which is an amazing probability-based classifier for basic text and sentiment analysis. But listen, out of all of these, there is one you absolutely need to highlight. Industry pro tip right here: make sure you start ensemble models on your study guide. Models like random forests and XGBoost work by taking hundreds of individual decision trees and mashing them all together. This prevents the errors of any single tree from completely ruining your results. Honestly, this is exactly how we consistently win data science competitions when we're working with tabular spreadsheet data. It's a game changer. Moving to the unsupervised section of your guide, you really only need to remember two heavy hitters. First, k-means clustering is your absolute go-to algorithm for grouping similar unlabeled data points together. If you ever need to segment customers based on their purchasing behavior, but you don't actually know what the segments are in advance, you use k-means. Meanwhile, principal component analysis, or PCA, is what we use to dramatically reduce the complexity or the dimensions of our data. It strips the data down to just its most vital information. It's a massive time saver for visualization, and it genuinely spares our laptops from completely overheating.
Moving right along to Chapter 2, Deep Learning Neural Networks. If Chapter 1 was all about neat, structured spreadsheets, Chapter 2 completely throws the spreadsheet out the window. Here, models use massive layers of artificial neurons, heavily inspired by the human brain, to tackle really messy, unstructured data like images, audio, and raw text. Memorize these architectures if you see unstructured data on the exam. You have multilayer perceptrons, or MLPs, serving as your baseline, one-way feed-forward network. But when things get highly specific, the architecture has to change. You've got convolutional neural networks handling computer vision for tasks like medical image analysis and self-driving cars. Recurrent neural networks, along with their more advanced cousins, long short-term memory networks, or LSTMs, handle sequential data like speech recognition. And finally, you have graph neural networks crunching incredibly complex networks of nodes and edges, which is perfectly suited for things like mapping molecular structures in drug discovery. So the absolutely crucial point here is understanding the right tool for the job. You can't just throw any neural network at a given problem. CNNs use highly specialized filters to scan across visual data to detect edges and shapes. They are looking at space. RNNs and LSTMs, however, rely heavily on their built-in memory because they are looking at time and sequence. They're historically used for language translation, where the order of the words completely dictates the meaning of the sentence. Next up is Chapter 3. Generative AI. This is all about creating brand new content. Now, flipping the script to generate entirely new content, you absolutely must understand this underlying concept first. Instead of just predicting a label or categorizing an image like we did earlier, generative AI models learn the underlying mathematical distribution of their training data so they can build something from scratch.
And attention mechanisms are the fundamental architectural breakthrough making all of this possible. Instead of reading a sentence one word at a time and forgetting the beginning by the time you reach the end, attention mechanisms allow these models to process entire sequences of data simultaneously. This lets them capture incredibly deep, nuanced contextual meaning.
With that in mind, your Gen AI study guide is packed with some absolute heavy hitters. Notably, we have massive transformer subtypes called large language models, or LLMs. Things like Gemini, ChatGPT, and Claude are just massive transformers trained quite simply to predict the next word in a sequence. And then you have diffusion models for generating images, GANs for creating hyperrealistic fakes, and variational autoencoders, or VAEs, which mathematically compress data down to its absolute core representation and then reconstruct it, which allows us to generate new variations of existing data.
Let's look a little closer at diffusion for a second. Systems like Midjourney, DALL-E 3, and Stable Diffusion start with pure random noise. Think of it like the static on a really old television set. They don't paint the way a human does. Instead, step by step, they sculpt the image by meticulously subtracting and carving away that static until a perfectly clear image appears. It's subtractive creation, which is just wild when you really think about it.
Meanwhile, generative adversarial networks, or GANs, operate on a completely different philosophy. They work by pitting two distinct neural networks against each other in a constant, endless battle. You have a generator, acting exactly like a digital forger, creating fake data, and a discriminator, acting like a digital detective, trying to catch those fakes. It's the ultimate game of cat and mouse. They train against each other, getting better and better, until the deep fake outputs are mathematically indistinguishable from reality.
Finally, we hit Chapter 4, Reinforcement Learning, the trial and error phase.
This is where things get really dynamic. In RL, models aren't handed static spreadsheets or neat folders of images. Instead, they are placed in the highly active environment and have to learn dynamically by trial and error. What is really fascinating about this process is how incredibly human-like the learning actually is. It's essentially how you would train a puppy or how you figure out a new video game. The AI observes the environment, takes an action, and then the environment gives it either a reward for a good move or a harsh punishment for a bad one. Based entirely on that feedback loop, the AI updates its internal strategy to maximize its points in the future. For the final section of your exam guide, lock down these 3 primary bullet points. First is Q-learning, the classic algorithm where the AI builds a literal table, a Q table, mapping out the absolute best actions to take in any given state. But simple tables completely break down in complex environments. So when Google's DeepMind famously built an AI to beat classic Atari video games, they leveled up and used Deep Q Networks, or DQN. The AI had to look at a graphical screen and make rapid decisions, so DQN beautifully combined that Q-learning logic with deep neural networks to process the dynamic screen space. Finally, we have Proximal Policy Optimization, or PPO, which is highly prized right now for being incredibly stable and efficient.
Make sure you write this one down, because this perfectly bridges the gap between our different chapters. Proximal Policy Optimization, or PPO, isn't just used heavily for teaching physical robotics how to walk. It is the exact mechanism used to safely align and fine-tune large language models. Through a process called reinforcement learning from human feedback, PPO is literally what stops a raw text predictor like ChatGPT from outputting total chaos, training it instead to be a helpful, safe, conversational assistant. And there we have it. You officially possess the structured cheat sheet to the entire topography of artificial intelligence, stretching from the neat tabular data of classical machine learning all the way to the dynamic trial and error environments of reinforcement learning. You've got the map, you know the core algorithms, and you understand the specific tools for the specific jobs. So the only question left for your exam, and frankly for your career, is which of these models are you going to deploy first? Thanks for joining me on this explainer. Keep studying those slides, and I'll see you in the data trenches.